going towards to more deeply in Solaris, and I would like to invite again scientific director of Solaris Synchrotron, and he would give us highlight not only about our beamline, but as he mentioned initially, Ukrainian community is invited for the beamline proposals, and I'm inviting Professor Marcin Sikora for his highlight on Solaris Synchrotron.
Thank you, Danilo. Can you hear me? Thank you for the invitation to this meeting. I really enjoy listening to the talks, and now I really would like to provide you with the brief overview what is Solaris at present, what infrastructure is available. I will very briefly show some highlights from different beamlines, but the two beamlines will be more focused talks after mine. So there will be Katarzyna Sowa from Polix beamline, which is micro spectroscopy beamline, and there will be Alexei Maximenko from the X-ray absorption spectroscopy beamline. So for these two, which are, I would say, the closest as a, let's say, the polygon to train, to learn how to use synchrotron facility for future Ukrainian beamlines, the two beamlines will be probably the best for you to apply. And anyway, I review the other beamlines that we have at Solaris. So Solaris belongs to LIPS, so we already heard about that. It's member of one of these accelerator-based synchrotron light sources in Europe. We are coordinating Nephews project that you already heard about before, with 8 targeted countries, where Ukraine is among them. So there is a preferential support for scientists from this country. We are the only synchrotron in Central Eastern Europe, which is located only about 200 kilometers away from Ukrainian border, close to the motorway and rather easy access to us. And we are proud to be future host for the Micro Nano XAS beamline of Light for Ukraine project. So the synchrotron is based in the southwestern part of Krakow, on the edge of the new campus of Jagiellonian University, that is the oldest university in Poland. It's about 3-4 kilometers from the city center. By tram is about 25-30 minutes from the train station. It's a third generation light source. It was designed with a lot of help from Max Laboratory, the team of Michael Eriksson. It was constructed from 2010 to 2015 from European funds. And now it's as a unit of the Jagiellonian University, but it's a national facility. So any scientist from Poland, but from anywhere in the world who is involved in research and development can apply for free experiments at Solaris. So we started our operation with 2 beamlines, the commission between 2015-2018. At the time I wasn't Solaris staff, I'm a brand new person, but I was involved in the commissioning of one of these beamlines, so I know the story quite well. And we operate from October 2018. And Solaris is financed directly by Ministry of Science and Higher Education of Poland, where most of the financial support is coming from. So when we look on we have 2 accelerators. So one is the linear accelerators that accelerates electrons up to the energy of about 550 mega electron volt. It's about 40 meter linear, 8 meter down under the ground level, and then we inject these electrons into the storage ring, but the nominal energy of the storage ring is 1.5 giga electron volts. That's why we have to ramp. So we do this ramping twice a day, at 8 in the morning and 8 in the afternoon. We ramp the energy from 550 to 1.5 giga electron volts, and the ring current nominally is 500 milliamperes, and it decays over time down to about 250. And we deliver the light from infrared up to the hard X-rays. When you look on the spectrum from the bending magnet at Solaris, the critical energy is about 2 kilo electron volts. That's the critical energy of photons. So as you see, the intensity, we are pretty good, especially in the soft and tender energy range. For hard X-ray, it's a little bit lower, but fortunately, thanks to the undulators like the one from PSI, we can increase a lot our flux in this architecture. So we have 12 sections, 12 bands, and 12 straight sections. For the moment, 3 straight sections are filled, and we have plans to fill with some other undulators that we will hear in a moment. So that's the current situation and plans for our facility. This is like a view of the old experimental hall with this extension that Luke was mentioning. And the instruments that are in the white background, there are operating instruments. So we have 7 beamlines and cryo-electron microscopy facility. There are also 2 beamlines which are operating that are for diagnostics, but we have some plans maybe to extend them also in future for scientific beamlines, like for example the LUMOS for UV beamline. In construction, for the moment, we have 5 projects, including the LIPS project of Light for Ukrainian, that we have funds allocated for that projects, and we have 3 quite well-developed projects that we are looking for funding. And in the next, I will review briefly all these instruments that are existing and our future plans. And if you want to see roughly the size of our synchrotron, this is like a football pitch, so you can see it's not that big. You can easily go around and just communicate with people doing different experiments. So we are like a small family of users and people involved in the operation of that machine. So if you want to see a very detailed beamline overview, then you can use this QR code to directly access our website, but then I will review one by one the beamlines that exist schematically where they are positioned. And the very first beamline that was operational from 2018 is the X-ray absorption spectroscopy for soft X-ray. We called it PIRX. The name is taken from the hero of one of the novels of Stanisław Lem, who is also the name of Solaris is also taken from title of one of his novels, Solaris, about the planet which is far, far away in the space and was researched by X-rays. So this beamline PIRX is devoted to soft X-ray spectroscopy, basically X-ray absorption spectroscopy, near-edge X-ray absorption fine structure, and also to the circular and linear magnetic dichroism. So the energy range roughly is from 100 electron volts to 2000 electron volts. And just to give you a flavor of one of the possible experiments, that's an example of the films, titanium dioxide films of thick of the order of 200-300 nanometers. The film were prepared for water splitting, and the thing was how to optimize their internal structure. So how to play with the parameter of the deposition that's the desired microstructure of the grains, but also the proper ratio between anatiles and rutile. So if you look on the titanium LH spectra, you can see that the spectra of these two aliphates of titanium dioxide, they have slightly different spectra, but the C1 and C2 peaks, they really differ a lot. So you can use these peaks as a fingerprints of the amount of anatiles and rutile in your structure. But also if you have titanium with different oxidation, not titanium dioxide, but titanium 203 or titanium oxide, the spectra is slightly different. So in this work in applied surface science, it was possible to probe several samples with different composition of the gases that were present in the sputtering chamber of magnetron sputtering. The sample were ex situ inserted into the analysis chamber of PIRX beamline and probed with high quality. And that was quite clear that depending on the ratio, if you look to optimize the amount of anatiles, you have to really go to high amount of oxygen in the atmosphere. So the other beamline that is closely related to PIRX is also soft X-ray spectroscopy, but in this case with microbeams. So we do microspectroscopy and also dichroism with 2 types of microscopes. So in this beamline, we have also the range of the energy from about 100 electron volts to about 1500 electron volts. But this beamline, the matter, hosts 2 microscopes. So that's why it's dual microscopy and electron spectroscopy beamline. The very first microscope is photoelectron emission microscope. So with the full field, we excite our system, and then we probe the photo emission spectrum, but with selectivity to different sides of our sample. So with in the a field of view of about 50 micrometer radius, we can see with the resolution of about 40 nanometers the chemical composition and also magnetic composition in this case of our film. So the example here is the films of iron of very different thickness, which were covered with antiferromagnet, nickel oxide in this case, and again with some ferromagnetic layer, this case it was cobalt, and then it is known that depending on the thickness of iron on tungsten, the easy magnetization axis is in plane or out of plane. And the question for this study was whether the cobalt on top will have also followed the anisotropy of this down film around here. And that was really confirmed that indeed when the iron has switched the polarization, also the cobalt film on the top. So this is kind of example for the spintronic application. And as you can see, this microscope provides you magnetic information with circular dichroism, linear dichroism, but also a chemical information, because you can tune to either nickel edge, you can tune to iron edge, you can tune to cobalt edge, and also see the distribution of these different elements in your sample. The other microscope that is operational at this beamline is so-called scanning transmission X-ray microscopy. So in this case, we have to focus our photons using Fresnel zone plates to very, very small size, to about 20 to 30 nanometers. And we scan, like in classical electron microscope, we scan our sample and we can measure both in transmission, and also we develop now the fluorescence and tachography. So that's basically the technique that provides you a similar information to electron microscopes, but with better chemical sensitivity. So one of the examples is, for example, these nanocubes that are the nanocubes of palladium that were filled with copper inside. And you can really see with this microscopy that indeed you see the copper inside many of these cubes that are the sample in the solution. Another beamline, so basically the next two beamlines I'm going to review, is the beamlines for angle-resolved photoelectron spectroscopy. So one of them is the Uranos, is ultra-resolved angular photoelectron spectroscopy, and here we work with the photon energy from about 8 to 100 electron volts with two normal incidence and plate grating monochromator for different energy ranges. And the typical example, that's how the beamline looks like. And the typical example, for example, are those these topological or Valley materials that you see what is the dispersion relation very close to the Fermi level. And here in this highlight, it was shown that depending on the stress given to the sample and the change of temperature, it was possible to observe topological transition in alpha tin, that it goes from this Dirac semi-metal with two nodal points to Weyl semi-metal with four nodal points. So this beamline has a very high resolution, especially in energy, but also in terms of momentum. And yeah, so I think it's recently also has installed the spin filter. So it's also possible to do spin resolve study, which are excited with photons of different polarization, not only linear, but also circular polarization. Another beamline photoelectron spectroscopy, angle resolved and chemical spectroscopy is the FELIX, is soft X-ray polarization and spin-dependent photoelectron spectroscopy. On that beamline, you can also do absorption spectroscopy because you can use the helical undulator, so you have very different polarization available, and the beamline is especially good for the linear dichroism. It also has recently installed spin filters, but it works in slightly different energy range. So that beamline you can consider already like high high photon energy excited photoelectron spectroscopy, because here we start from about 50, 70 electron volts, and the useful energy range is about up to 1800 electron volts. And the range depends slightly on the polarization that you need. And the example, that's how the beamline looks like. It's quite a complex beamline. There are two preparation chambers, so many things can be prepared in situ. There is also a special chamber with UFO, we call it, that you can attach your own chamber if you want to prepare something on site or deliver your sample for some additional preparation. And then on this beamline, you can use very high excitation energy, up to 1800 electron volts, and then you can probe very deeply because the kinetic energy of the electrons is getting higher and higher. So the example that I'm showing here is the example of perovskite film that was deposited on titanium dioxide. So scientists here, they were able to observe not only the electronic structure and composition of perovskite film with photoelectron spectroscopy, but also they are able to reach the titanium dioxide substrate, and especially the interface that is formed between perovskite and titanium dioxide. Yet another beamline is a POLIX, is polycapillary X-ray optics and polychromatic X-rays. It's the beamline that operates in hard X-ray energy range, but this one will be very nicely presented, and you will see more results and highlights by Katarzyna Sowa directly after my talk. And another beamline in operation is Astra, which is for the X-ray absorption in tender energy range and hard X-ray energy range. These two beamlines, the recent ones, they have photons from the bending magnet radiation. They were recently opened in 2022, 2023. And for Astra, there is application of many different X-ray spectroscopy measurements. There was also recently installed Raman probe, so you can characterize your material, perform some operando experiments. So Alexei Maximenko will present the opportunities and highlights of that beamline. What else we have, which is also available for users, is cryo-electron microscopy facility. The free of charge is the access to cryo transmission electron microscopy for protein characterization and biomicromolecules. There are two modes of operation: is the single particle analysis and tomography, and it's very high resolution. We also have another cryo-electron microscope, which is called Glacios. This one, at least until next year, is paid access, but this is very good for screening of the samples. So if you want to be sure that the sample that you prepared is good for cryos experiment, you obligatory have to screen it. And you can do it at any microscope, of course, but Glacios is something that we offer for the users to find their best samples for a high resolution electron microscopy pictures and investigations. And the beamlines that are in operation and partly in commissioning because there is not yet photon flux from the synchrotron delivered to the instruments, but you can already use the three different instruments for infrared spectroscopy. So chemical infrared imaging and chemical infrared spectroscopy. We have three instruments with TIR, with SNOM, and the IFM enhanced with a synchrotron beam. And this beamline is completely different energy range, of course. It's from the fractions of milli-electron volts. So it's from the infrared up to the visible light in operation. And the beamlines under construction. So I show them in the series. So the first series are the beamlines that are devoted to bio study. So one is the small angle X-ray scattering beamline that is currently constructed by at the section 02 BM, so that will be a neighbor of the Light for Ukraine beamline. And the next beamline for the new experimental hall is ARIA, which is the beamline for macromolecular X-ray crystallography, so high throughput beamline for the X-ray diffraction experiment on molecules. We have the project of Light for Ukraine that Luke was very nicely presented just before me, so that will be in that section. And there are some other projects that are ongoing. So we have Operando and Station for the hard X-ray beamlines that in future we hope to move to one dedicated beamline around here. There is also a branch for near ambient pressure X-ray photoelectron spectroscopy constructed at the moment at the Felix beamline. And we also have a plan for extension of our user laboratory and helium liquefier, because the consumption of liquid helium for low temperature measurements is quite high at Solaris. And there are the beamlines that we have in project phase that we would like to develop soon. So it's ambient pressure, hard X-ray photoelectron spectroscopy, which we hope it could be like one of the end station of the Light for Ukraine beamline. And there is also the plan for XRD and wide-angle X-ray scattering, which could also be combined with operando spectroscopy. And there is a plan for beamline in collaboration with Kielce University for the high-energy resolution spectroscopy with hard X-rays. And one of the almost last slides of mine. So if you want to be a Solaris user, if you would like to use this infrastructure, you're very welcome. For the moment, we have nearly 2,000 users registered in our system, Solaris user network. Many of them are Ukrainian in origin or less in affiliation, unfortunately. We have many Ukrainian scientists from Krakow, Slovakia, but we also had like Ukrainians from Kiev, and we invite you all to come to write your proposals. We have 2 calls twice a year, so the deadline beginning of October and beginning of April for standard, for 1 experiment, and long term up to 3 experiments in a row. For proposals, the access is free of charge. It's peer-reviewed proposals, and via Nephews, it's possible to pay for the travel costs and staying during the experiment. We also have a rolling call for short experiment, let's say test experiments. You are not sure if your material is good for synchrotron. This experiment can also be mail-in or remote. It's after agreement with the beamline supervisor, but on many beamlines, I think it's possible. So if you cannot leave country, you can think about submitting a proposal for this rapid access. And there is also another ways of access to Solaris via CERIC-ERIC consortium that we deliver. About 10% is a consortium of Central European research infrastructures, not only synchrotrons, but many different research infrastructures that also covers the travel costs. And there is a very special grant, RIANA, that is dedicated to nanoscience and nanotechnology that has just started under LIPS supervision, and it also covers the cost and access to many synchrotrons, not only Solaris, but many synchrotrons and other infrastructures in Europe. And a little bit of the statistics. So since the beginning of our operation, we have more than 1,300 of proposals with about 350 publications, and we are national facility for Poland, but we really invite foreign scientists. So more than 25% of project leaders of the proposals that are performed at Solaris are foreign scientists, and the acceptance rate is not that high, not that low. So about 50% is a chance that your proposal gets through. And we are not sure how to do it. We have a very nice user office. It's not it's trying their best to help users, future users, to be prepared as best. They even prepared this very special way of guide, like a game, to tell you what exactly you have to do at each step of sending the proposal, preparing your experiment. So with this, I would like to very welcome you on behalf of all the Solaris staff in our place. That's most of the Solaris staff, and we hope soon you will be close to our gates. So feel invited, and I'm asking for your questions.
So any questions? I think Professor Colin has question.
Hello, Marcin.
Hello.
Actually, a few technical questions. First, do you plan to switch to top-up mode sometime in future?
Yes, we're discussing that, but actually it's quite expensive for us because the Linac we have has a limitation in the length and we cannot extend it much. So there is a plan, but we would need to like replace, so fully refurbish our Linac. So we have these plans. We hope to, but not we don't have money, so we have to plan it, and unfortunately that will be quite expensive. So you want to maybe also to connect it with some other developments, maybe to have some beamlines at the end of LINAC. To be fair, what would be the time frame for this? I wouldn't expect it before 2030, but we would really like to at least start this top up, let's say, campaign in about 2-3 years from now, to be ready maybe after 2-3 years of operation of the Ukrainian beamline. We hopefully will be ready for top up, which I know would be much easier for many experiments. Yeah.
Okay, thank you. And I wondering about NIM usage at Uranus. Do you know
Yes.
how often it is used? It is much lower intensity, but how often it's used?
To be true, I don't know. I can ask and maybe I can give you the direct answer, but yeah, I would have to check. I mean, uh, I would say it's about 50-50. It's because for the higher energies we have this other beamline Felix. So I would say more the experiment concentrate on the Uranus on using NIM. I also know that there are experiments that use both, because on one experiment you can just change the energy and to probe the Z momentum, yeah, with the energy. But yeah,
That usually it's difficult to use NIM for the same samples as you use PGM because density is much lower.
yeah, I agree. It's much longer experiment with NIM. Yes.
Maybe it's still possible. Okay, okay, thank you. Maybe more.
Thank you.
Marek, Marcin, I
Yes.
have a question. Do you have any development concerning small gap capability for the storage ring?
Yeah, that's a good question. Uh, for the moment, it's not much of the developments for the storage ring ongoing. So what we plan is just to, the very first in the hierarchy is the top up. And then depending how that works, we would see how our beam is behaving in the storage ring, and then we could think about the low gap. For some time, we were planning also the superconducting undulators and maybe like magnets, the very strong magnets. And one of the beamline area is also being constructed on the magnet that are very close. Is this phase shifter? Yeah, it's kind of wiggler. But the development's not anymore. So that's what you know is more or less what we have for the moment.
But maybe the top up is actually a good motivation, or the small gap is maybe a good motivation for the top up.
For top up, yeah, because top up definitely would improve the size of our beam, because we don't have to ramp, yeah, so we can optimize everything in the ring. That's true.
Yeah. Okay.
Thank you.
Okay, thank you very much, Marcin, for this wonderful talk. And now we switch more deeply into Solaris. Okay, sorry.
A very small one. What is the time concerning those the proposals for the joint collaboration studies that you mentioned, right? The two calls per year, right? Is that
yes?
And what's the timeline for that? Like, say, from the proposal to the actual work at the beamline, how many months, years, well, hopefully months between?
Okay. Yeah, so I understand. For standard proposal, the one that you submit either in September or in March, usually the committee meets in about 2-3 months, and the beamline is delivered in the next semester. So if your proposal would be submitted last October, you would know in December, so in 3 months you would know whether it got accepted or not, and the experiment would be scheduled from March to July. So it's in about 6 months, roughly, from 4, let's say, to 8 months. We have also this access for the rapid. It's very short experiments, usually one shift, so 8 hours, sometimes 1 day, and that's much faster. But we cannot really promise that definitely will get beam, because it depends how many proposals of this kind we have. But sometimes it's even possible in 2-3 weeks from the moment that you submit the proposal that you may get beam time. More typical, it's about 2 months, but this is mainly for tests or something that is very, very important scientifically. I mean, the details are on the website, but the typical access is about half a year after submission of the proposal.